All right, well, to second meetup for the zero knowledge study group, and yeah, I'm very glad a lot of people showed up for the first one, and after we upload the video, it seems quite many people are interested, so we're going to keep learning together. So, any other like high-level comments before I dive into details today? It's good. It's good. Okay, that's good. All right, let me share my screen. So, okay, can you see my screen?
Yeah.
Okay, that's good. Okay, just a recap. I think last time we introduced some fundamental ideas about zero knowledge in specific to this specific zero knowledge protocol called the ZK-SNARKs. Okay. Somehow so. Okay, Brandon is joining again. Okay, anyway, so we talk about how we talk about how the ZK-SNARKs works, and also give a few examples, such as Zcash, Tornado Cash, and some of the ZK games we have introduced. So last time we mostly focus. So for ZK-SNARK, usually people leverage it for two purposes. One is so-called privacy, right? So you want to put something, you want to commit some information onto the blockchain, but you don't want to everybody to see it, right? So the standard way to, you first, put a hash, which is like cryptography, it's a cryptography technique to commit to something so you cannot change it later. And then later on you prove the pre-image, and then you can manipulate the state. So this way, you can commit to the state, but also you can verify the state transition is valid. And this, other than the privacy, I think that's another big thing about the so-called ZK-SNARK is, we talk about the ZK part, but there's also a big one we mostly focus on today, which is the S part. So basically means succinct. So what does succinct mean? Basically means, we talk about two things. One is the proof size, right? Meaning proof size very small. How small? Usually is, if the n is the complexity of the computation we're trying to prove, you can think of roughly is log n or polynomial of log n. And some of the schemes, you can even be constant. Basically, it doesn't matter. It's a big old one. So doesn't matter how complex the computation is, it is constant size. So that's one thing, the proof size. And the other thing we worry about is how fast, how long does it take to verify the proof? We also want that to be fast, succinct. So usually two things, small proof and quick verification. So this makes it ideal use case for in the blockchain space, right? Because usually when we talk about you do computation or put data on chain, because it's still much more expensive. I mean, even in Bitcoin, right? It's scalable, so it's very cheap, but still much more expensive. I think it's many orders more expensive than if you do it on chain, rather than compared to off chain. For example, you do a SHA-256 off chain, almost free, right? But if you do it on chain, it's not quite free yet. So you still have to pay a huge price. I mean, relatively. So we want to leverage this succinct list to do the so-called verifiable computing. So what does this mean? So if you have a computation you want to prove, and so you give it to prover, the prover compute it, not only give you the result, but also give you a very short proof. Hey, this computation is done correctly. So you can easily verify it. You don't have to rerun the computation. You can just take the short proof, run the verifier very quickly, and see if it's if the prover is doing something fishy. So how we leverage here, I think one of the famous example, in the blockchain space, everybody is talking about, rollups. So we want to use this example to demonstrate how using ZK-SNARKs to verifiably, run some computation. How many? So just something quick. How many of you heard about this term before, rollup, in the blockchain context? Anybody heard about this?
Yeah, a little bit. It seems to be the approach Ethereum is really leaning on.
Yes, I think they have. Yeah, every few years they use some new term for scale. But anyway, it's a rollup. It's almost like a literally means roll up. So you think about, you have a few let's say transactions. So how does a transaction gets processed usually, right? You can think of, logically, you can think about it almost like the state machine. So each blockchain, you have a global state right there, right? Let's say you have in this graph, so you have state 1, which is the old state, and then after you have processed, you can a few transactions, the state is going to be mutated, go to the new state. So go from state 1 to state 2. So usually how you go from one state to the other, you pretty much, you just, you send it to the miners. The miners just check all the, process each transaction. Each transaction mutates some part of the state, right? So then you go to the next, and then you get another transaction, you mutate it, and then you go to the next one. So in the Ethereum model, right, because it's count, so, and it's global state. So you can think about this state as a global state, and each transaction is just any Ethereum transaction. In the Bitcoin space, right, this state, you can think about it as a UTXO set, right? So you have all the outstanding UTXOs set, and then once you have transaction, you pretty much, you spend some, you close some old transaction UTXO being spent, and then there's some UTXO being created. So you pretty much delete the UTXO spent, and then you add into the set of all the new UTXO you create. So logically, you can both, models can be modeled in a state transition function. And then the bottleneck here is you have to, if there's a lot of transactions coming in a short time period, right? So it becomes a bottleneck to process all the transactions. That's why I think you see a lot of transaction blockchain, they have the so-called scalability issue, because, it takes some time to process its transactions. So what if you can, if you're a miner, you actually don't care too much about, what exactly this transaction is doing. You just want to make sure, okay, all these transactions, mutate this state from 1 to 2. And I just want to make sure, this transition is following the rules. I don't specifically care all the details. So what that means is, instead of process transaction one by one, what if you can say, you have state 1, you have state 2, and then I also give you in the middle all the let's say 1,000 transactions. And I just then, with this, I also give you a proof. Hey, if you do start from state 1, if you process all these 1,000 transactions, you are going to end up in state 2. And then I can submit this proof to the blockchain. So the blockchain doesn't see all this, all these transactions here. You only see, hey, this proof is good, and then I can transition from 1 to 2. I don't care about all the details about all these transactions, which may be complex, right? Because you can think of, they can be doing very sophisticated smart contract here, but I don't actually care. If you just want to make sure that this state, basically this state 1, if you play them all this transaction 1,000 transactions from the beginning to the end, you're going to end up with state 2. That's one way to do it, right? So you pretty much rerun all the computation. But what if I don't want to do that? I kind of roll all them up, right? That's the roll up thing. I want to roll them all up, and put one just single proof. Hey, say if I do this offline, off chain, I give you this proof, then I can prove, hey, I have all these transactions such that if I start from state 1, I'm going to jump to state 2. So the blockchain doesn't have to process, all these transactions. You can just verify, as we said before, right? The succinctness, make sure the proof is small, and also the verification is very quick. So instead of doing all this transaction processing, I can just verify this very short proof. And then if it's good, I jump to the, the next state, which is equivalent to just natively rerun all these transactions. So that's a basic idea for Rollup. So you can potentially scale, right? Does this make sense overall?
So can you relate this to like a UTXO model? So in state 1, if I have like UTXO for some address A, and then the final state B is like those Bitcoin are at address B. Could these like off-chain transactions go anywhere as long as B ends up with the Satoshis at the end? Is that the idea?
Yeah, I think logically that's the idea. Basically, state 1, you can think of, you have a set of, in the Bitcoin context, you can have a, UTXO set, right? Let's say UTXO 0, 1, 2 to 10, right? And then you have, let's say, transaction 1. Let's say you spend transaction 0, and then you create UTXO 0 and create another UTXO, let's say 11, right? So this is going to be UTXO 0 to 10, and this transaction spend 0 and give, create a new one, let's say UTXO 11. So this new state is going to be UTXO 1 all the way to 11, right? So in this case, I think I'm using a little bit of an analogy, but that's why it breaks down, because if it's just UTXO, the Satoshi UTXO, because this is not how the miners do it right now, right? There's no UTXO rollup. So think about it more like a more abstraction on top of it. Let's say a token, right? Let's say you have a token. You have this set of tokens that's not, that's outstanding. On top of the UTXO set, right? You have tokens that's not spent, UTXO token set, and then you have all these token transactions, right? Sending from A to B, B to C. You can all roll them up, so you can you can make sure all this transaction. After you have all this transaction, that you have the new token balances. Does this make sense? So the native UTXO, I think that the analogy where it breaks down, because that's how not the miners now, they are not verifying the proof. They just see all the raw transactions. But if you talk about anything you can build on top, let's say tokens, you have this model. Does this make sense?
Yeah, that makes sense. And another question, if I remember from last week, you talked about the proofs were probabilistic. Is that correct?
Okay, let's go back. So in theory, some of them, yes. But in practice, for all practical purpose, you can think about this as, as non-probabilistic. Why is that? Because let's say, the ZK-SNARK that's that's used by us right now, or by Ethereum. So basically, you have it is probabilistic in the sense that, eventually they check some math, and the math is such that if you say, if you create a proof, you have what's the chance of, it's almost like a hash collision, in this sense is, you have, let's say, you have 2 to the power of 256 possibilities. And then without knowing the witness, you may choose some random number that make sure even you don't know the witness, somehow the verifier, you fool the verifier. But the probability is almost like in the realm of like hash collisions. Let's say 1 out of 2 to the power of 256. So in that sense, it is probabilistic. But on the other hand, right, for all practical purposes, you can think about this as this is not going to happen, right? It's almost if you create some random Bitcoin private key. I mean, it's possible, you know, in theory, you are going to end up with an address that's with somebody else, right? I mean, given there's no software implementation bug, you actually generate randomly, and you happen to have the same key with somebody else, and somebody else happen to have some Bitcoin in this, you know, in this private key. So I mean, in theory, it's possible, but for all practical purpose is impossible. You see what I mean? So in theory, it's possible, but the probability is so low. For all practical purpose, you don't worry about it.
I get it. Okay.
The thing about it is that it's almost like you generate a private key, you're going to collide with somebody else, or you generate a SHA-256 hash. You're using different pre-images, you end up have a collision. I mean, it's possible, but for all practical purposes, we don't worry about it. It's too small, too small. Go ahead.
Shall we, staying on this diagram. So in the case of validating token state transfers, and if the tokens are public on a public blockchain, and if W, in that case, W does not have to be, we don't need a private W.
Yeah,
I think you had mentioned from last week, and then we could publish these proofs for anyone to anyone could publish the proof and anyone could validate.
Yes, the proof is always public. So only thing that may not be public is the witness. You may have a witness, but you may not, depending on the use case. So for example, the one we talk about today, right now, right? When you roll out, if you only want to scale it, you don't have a witness. But let's say you have this token set, right? You want to just scale it, you just make it fast, process more, right? You don't have to have a witness. But if this is a token, let's say you want to hide some information, right? You hide the sender, the receiver, or the amount, then you can put it in the private witness part, and then you will know. Then the outside cannot know. Only the token holders know all this information. So it's a choice, depending on whether you want to hide them or not. But you can always hide them if you want. Okay. Anything else? Okay, let's go back to the current slide. So in this case, right? So for example, let's say you have a token solution. You want to build a, let's say, a scalable token contract on top of this. So this is a contract. What usually happens, I think, yeah, let's actually, use a, okay, let me share this slide, not slide, this page. Okay, can you see this page? Okay, can you see?
Yes.
Okay, the ZK rollup, this is one that shows up. You see this? Everybody?
Yeah.
Okay.
Yeah.
So, if you want to check out the more details, check out our articles on ZK rollups. We do it on Bitcoin. So usually how it works is, you have, I think this is how Ethereum, but it works the same way as on Bitcoin. So basically, you're going to, if you want to have a rollup, you're going to have a almost like a master contract. Let's say you call it a rollup contract. And let's say in this example, we want to create a token contract, but we want to make it scalable. So we use rollup. So we use multiple token we roll up multiple transfer transaction into a single one and then attach it with a proof. So how it works? So you first deploy the rollup contract. So think about this almost like the contract that's going to pretty much the verifier. Okay, so it also have some state information. We talk about here, right? So how do you maintain the state? One way is to, you put all the, token owner. Basically, you have let's say fungible token. You have all the token owners and the balance. But usually people don't do that, right? Because as you put more and more, it's going to grow, right? So if you, for two purposes, you may want to hide it. One is you want to, save space, right? You don't want to put the whole table. It can be big once you have millions of users. The second part is, you may want to hide it, right? You want to make it private. So for two purposes, a lot of time you don't put the, the state directly. You put the hash. You pretty much put the whole contract into a Merkle tree. So you only commit the count root in on chain. So outsiders, they only see the root of the Merkle tree. So each root is, you can think about it's like each token owner. So you have let's say you have public key, you have the balance, but you can have some other meta information. But you can just say who owns how many, and then you put this into the state root, and then the rollup contract only checks, right, whether, so now I have an existing state root, and then you give me some more transfer function transactions coming in. What's my next state root, right? So that's how, if you don't forget about all the rollup zero knowledge thing, that's how it works, right? You have a old state root, and then you have new transactions coming in, and each transaction is going to mutate this root. Then I'm going to have a new root. So that's how the, a non-rollup, token contract going to work. But what if, I want to use rollup to speed this up, right? So the way you do it is, let's say you have, each transaction is going to, let's say, you can make some deposit, you can transfer, you can have withdraw. It's going to mutate this, the root of the Merkle tree, right? So that's every single time you are doing this transaction. So actually you are verifying some kind of computation. In this case, what's the computation look like? So you may say, hey, if this is the value transfer from Alice to Bob, right? So you may check a few things, right? First, you want to check, oh, does Alice have this many tokens, right? You make sure the balance is good enough. And also, oh, is this authorized by Alice? Meaning you can check the signature. And then you can check, hey, does Bob get incremented, balance get incremented by this much? And also, does all this, afterwards, does all this, the new state root, because you can pass the Merkle path and you can make sure the state root is, updated correctly, right? That's how you're going to, if you just run natively, don't worry about rollup. That's how you're going to check it, right? So in the rollup, instead of doing this, in the contract itself, you verify all this off-chain in a ZK-SNARK. And then ZK-SNARK is going to, eventually produce a proof saying, hey, all these transfer functions is run correctly. So it's going to, instead of each transaction of them, let's say, for example, you have 100 transactions. You're only going to have, the proof say, hey, all these are good. And then you can update the state root correctly. So even, I think later on, we are going to look at the specific, the proof in some of the code, but right now you can just look at the high level. That's exactly what I just talked about. You check, this is the computation you are proving, right? You check up quite a few things here, but you can also put here in the circuit you are trying to prove. So eventually you're going to only have one proof, but this proof is going to prove with, even you can almost think about this proof is, usually when we talk about digital signature, right? You think about this like integrity for some data, right? You use a signature. And then the ZK-SNARK, this short proof, you can think about almost like a proof, but for computation instead of for data. So is this, if you have a digital signature, make sure, hey, this message is correct. But if you have a, let's say, zero knowledge proof, ZK-SNARK proof, you are saying, hey, this computation is correct. So you can, this is a good analogy to simplify the, at least for my understanding. So in this case, you say, hey, I have a proof all this transaction process is correct without rerunning the thing. You only have to check the proof. If the proof is good, you know all this transaction is valid. Make sense so far? And the way you roll up it is also very easy, right? So here, you only process one single transaction, right? But you can always chain all these transactions. So instead of doing one verification, one transaction, you can just put them in a loop, right? So you can say it can be 1,000, it can be 1 million, it can be even 1 billion. So but the only downside is, of course, the bigger the computation is, the longer you are going to take to generate the proof, right? But the good thing about this is then whatever ends up on chain is going to be much, much shorter than if you run this billion transactions on chain natively. It's going to be much, much smaller. It's exponentially smaller. Or sometimes it's just 1 billion times smaller because the verification can be big or one, can be constant, or at least log of n. That's how the rollup goes. Why rollup can speed up, because even if 1 billion transactions, if you can somehow produce a proof, the proof is always going to be like 1 milliseconds or 10 milliseconds. Doesn't matter how many transactions you have. Does this make sense? Okay. Yeah, I'm not going to jump into the kind of the code here. That's what I'm going to cover next. So anything else before I move on? Okay, if not, let me switch back to the slides. Can you guys see my slides now, or you are still seeing the page? Okay, that's good. So we talk about a lot of theories right up to this point. What kind of properties you can leverage for this specific, the most popular ZK protocol out there called ZK-SNARK. So you can use it either for privacy, you can hide because you can have your own waitlist, only you can see. So you can use it for a lot of either private payments or so-called anonymous payments, or you can use it to hide some kind of information. Only you make the commitment on chain, but you can still verify it, like all kinds of a partial information gain. Or you can use the Succinctness as part to do verification for arbitrary computation complex. So this is especially appealing if you have a huge computation, very complex. It may take you like a year off chain, and you may even run like a few data centers to run it. But it doesn't matter. If you have the proof, it's going to be like few hundred bytes or maybe several kilobytes. You can still verify it within milliseconds, even in your phone or browser. So in the blockchain space, a lot of people use this to do the so-called rollup. Basically, you batch all these transactions and you produce a single proof. And if this single proof is good, all these transactions have been processed correctly. So we cover all this theoretical background, but then at the end of the day, for this subgroup, I think at least at the beginning, we want to be more focused on all the application side of things. A lot of us are here, developers are watching or here live, or maybe later on the video. They just want, now we have this good theory, but how do we, apply it in practice? Where to get started? I think that's one of the bottleneck for ZK adoption. I think, how do we get started? So for here today, for the rest of this meeting, I think I'm going to walk through like a very simple example on exactly how do you prove some computation. Okay, so we're going to use this high-level tool called ZoKrates. It's like a fun wordplay from the name. Of course, you probably already noticed ZoKrates. So you use a ZK, so it's a ZoKrates instead of Succinctness. And this is a tool set that's actually originally developed for Ethereum, but later on we are going to cover, hey, now we have adapted. We can also use it on Bitcoin. So what does ZoKrates enable to do? It enables, if you're just a regular developer, you come here, you don't know anything about, all the theory of zero knowledge, but with this tool, you can program the program you want to compute in some kind of like a Python-ish. I think I'm going to show some code later on, but it's very similar to like a Python. So if you know any high-level language of the today, you probably can, pretty readable here. So you have, you can define some function, you have some variables, you can put some assertion on top of it. You can have, you can do all kinds of operations on these variables. But let's first focus on the, little bit of abstract at the high level. What does it do? So basically at the beginning, if you have some computation you want to verify, for example, you want to verify you have, some solutions to some Sudoku problem, or you want to say, hey, I know some pre-image to some SHA-256 hash digest. I want to prove, but don't want to tell you. Or you want to say, hey, I have this, this transaction, that transaction, and it's processed correctly, as in the rollup transaction, right? So you first code, in this Python-ish, zero knowledge language, also called ZoKrates. It's for the language, but also for the tool. It's also called ZoKrates. You program the computation you want to prove in ZoKrates, and then you go through this process. So this process at the beginning, it may look like, super complex, right? Because there's a lot of steps and a lot of arrows, and yeah, it's a little bit of maybe a little bit overwhelming from the beginning. But I want to remind you, always go back to the, last time we spent this most of our time on the slide. I talk about, ZK-SNARK, the theory, the 3 steps, right? So you can see once you understand these 3 steps, it pretty much maps exactly to here. So who can tell me what the ZK-SNARKs, the 3 basic steps here? Anybody wants to try?
So it's the setup, generating the proof, and then verifying.
Correct. So here I'm going to show you how all this many steps looks like a little bit convoluted, but actually if you boil it down, it basically give you the 3 steps there. So the first one is so-called setup. So the only thing is, that when you set up, right? So this setup, this specific tool, it takes a very a low level circuit representation. As I said, usually you represent your computation a lot of times in so-called circuit, almost like the electronic circuit in our hardware, but it's called a arithmetic circuit. So basically you only have multiplication and also have addition, and you also down in some instead of normal integers, you have a prime field. Basically you are doing modulus, but that's all this very theoretical, and it's very hard to program for programmers to write, let's say, to convert the thing they want to prove into so-called arithmetic circuit. So that's why instead you have the ZoKrates high-level language. So you don't have to do all this, low-level programming. So you can write your programs in almost like a Python-ish code, and then that's a compiler that compiles to this, circuit. This is pretty much, you can think about this as a circuit. Now, once you have the circuit, right? So basically, this circuit, if I can, let's say, if you still can remember, the setup takes 2 inputs, right? What are the 2 inputs for if you have when you set up? Anybody still remembers? So okay, we can, quickly okay, let's go back here. So what are the 2 inputs here? You have the function you want to prove, and also you pretty much have the random number, right? You have the entropy, which is also called the toxic waste. I think of this. So when you set up, you have two inputs, right? The circuit representation of the function and also some randomness. So that's exactly what happens here. So you have, when you have setup, you have this is the f, the function here, right? In the form of circuit. So of course, it's internally, it's going to generate some randomness. So you're not going, that's not explicit lambda here, but you know it's going to be here. So what's the output for setup?
So two keys, the proving key and the verification key.
Exactly. So that's exactly what happens here, right? So once you have the function coming in here, you have internal some randomness, you're going to have generate a pair of keys, the proving key and the verification key, right? So that's, you know, from here, 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 you can see this is the setup, right? This is the setup phase. And what's the next step? The prover, right? That you want to generate the proof. So that's what the prover side is going to do. So you have, now you have the proving key. So then you are going to have the witness here. I think that's one additional step here, means compute witness. Basically, you have the circuit. You can think of it, you have the circuit. You only have the input and output, right? So that's one additional step here. You pretty much, you know, the generate the proof is almost like a, okay, let's first cover this part, right? You generate proof. Again, you need two inputs or three, right? So you need the prover key, the public input and the private input, right? So, and then the output you're going to have is a proof. So let's go back here in practice. You have proving key, you have the witness, but of course, yeah, sometimes you can probably have the public output. I think which is not drawn here, but with these three, you can generate proof, right? Make sense? Okay.
Yeah. So that proof would be some client that, you know, is holding some secret data.
Yes. That as I think most times you have, but you can also have the, you know, some special case you don't have a secret data. So let's say the rollup, you don't want to hide anything, you just want to speed up. So the witness is always optional. But in most cases you have a witness, yes. So only one thing I think additional step here, the surprising thing is you have a computer witness step here. So the witness, you can think of, you know, you have a circuit, right? The circuit, you have a gate, you have input and output. So at the beginning, at the very top, you only have the public inputs, right? You only have the inputs at the very beginning for the whole circuit, right? So that's why you need this additional step to compute all the intermediate circuit value. Does this make sense? So you can have the witness. The witness here is not the, you know, the input witness to the circuit, but also for all the intermediate gates as well. So that's why you need to like this is almost like can be part of the generate proof, but yeah, somehow I think maybe some cases you may want to debug or something, you need this additional step. So basically think about this plus this is the prover function in ZoKrates, this framework. If you don't want to, yeah, you can if you even forget about this step, I think that's fine. You can think about these two combined together, give you the proof. Make sense?
So the compute witness has to be watching the comp.
Go ahead.
Yeah, the compute witness has to be watching the computation off chain at all times.
Oh, this thing, you know, everything we talk about here is off chain so far.
Okay.
Okay.
But it has to be watching all the steps that goes into
the circuit
generating the circuit as it executes.
Yes.
It witnesses. Okay.
Yeah, that's what it is internally, but we just use, I think in next slide, I'm going to walk through this example, how to get a better idea. Okay, this is step 2, right? You generate the proof. And what's the last step? It's, of course, obvious, you verify it, right? So you have the options. You can verify either off chain, they have that option, but here we only show one. You can verify it in a smart contract. Basically, once you have the verification key, you can almost let it automatically generate the verifier program in, I think for them, either in Rust or in Solidity. But we also extend it, so you can also export the verifier program in script as well. So that's how you can deploy on Bitcoin and then verify it. So once you have the verifier, right, you're going to have, you can check then you can verify the proof, right, using this algorithm here. So basically you have this, and this, then you can check whether this proof is good or not. Make sense? But here that's not shown. It only shows, hey, how do you generate the prover, the verifier program? Okay, I think so this is a little bit theoretical, but let's walk through one concrete example. Hopefully this will clarify things up. Okay, so on this side, I'm going to show all the command line tools. Basically, this is the CLI tool, but they also have the JavaScript escape. But for here, just for demonstration purpose, I'm going to just use the CLI command line version. So let's say I want to prove, in cryptography or even in blockchain, right? So a lot of times when we even generate the keys, right? We have a lot of times we are relying on some assumptions. And one very famous assumption is saying, oh, it's very difficult to factorize, a big integer if you don't know the secret, right? Because you can always produce two. Yeah, it's a so-called RSA assumption. So basically, if you have a composite number, which is big, you can have 1,000 bits or whatever. And is multiplication of two prime numbers. And if I don't tell you these two prime numbers, it's very difficult to, it's very easy. If you have two prime numbers, you multiply, you get a big number. But if I only tell you this new big number, it's very, computationally almost impossible to reverse, to find these two prime numbers. Okay, follow me so far? Okay, so, just give a very simple example. I would say, hey, I know the, two prime numbers. I know the factorization for this big number. Okay, Alice said, I know this answer. Bob said, yeah, tell me. But Alice may say, hey, I just want to tell you I know this, but I don't want to tell you exactly what these two numbers are. But I can prove to you I do know these two numbers. So how's that going to happen? So of course we use zero knowledge, and we decide to use ZoKrates to prove it. How do we prove it? So again, it's pretty readable here, right? So you have, say, the public, you have all these inputs, right? Again, set up a prover function, right? You have two type of inputs. If you don't put anything, it's going to be public, right? This is n. Basically, this is proving I know two numbers, P and Q, which is going to time together will give you this public big number, n. Okay, I know the factorization, but I'm not going to tell you these two numbers. So that's why you put two keywords, private and private, in front of the declaration here. So what am I going to prove? Of course, first, these two times together give me n, right? That's how we prove we know the factorization. But also, we want to make sure this is nobody's cheating, right? Because you can always say, I know 1 times n. It's always going to n, right? But that's not the factor. You want to make sure they are not equal to 1, or you can say larger than 1, right? So assertion is like any other language. Basically, if this condition does not hold, the whole thing will just fail. Will just fail, right? Is this readable to you guys? Okay. So once we code this in so-called ZoKrates, we can save it in a file. Let's say I call it factor.zoc. So what we are going to do, we're just pretty much just, run exactly the steps we talked about in the last slide, right? So first, we're going to compile it. We have the high level code, but we want to compile it. They call it flatten here. Pretty much we want to flatten it in, we compile it into the circuit, right? So you can first compile it. So once you have the compile, you can set it up. Right? So I think all the parameters, they are all, using some default parameters. I'm not going to show all the command line options here. It's going to be, so basically you can have some default names. So once you have compile, you're going to, let's say you're going to have some intermediate circuit called a.circle, circuit, whatever. And then this setup is going to take that, by default, it's going to pick that up. So basically, when you have the setup, you have this, let's say factor.circuit is going to have generate two keys, the prover key and the verification key. And also, this is going to be non-deterministic. Basically, you have the entropy, the lambda. So this, even you have the same circuit, if you run 2 setup, 3 setup, it's going to all generate a different pairs of keys. Okay, this is the setup. And again, this finishes the setup, right? Step 1, step 2. And then this step and this step is going to generate the proof. Again, as I talked about, the first step before you, formally generate a proof, you're going to run compute so-called witness. So the witness -a is, this is basically the arguments. So you can think about this, that all the arguments to the main function. This is P, this is Q, this is N. Basically, P, Q, N, right? So if you do the simple math, I give just simple example, 7, multiplied by 13, give you 1993. Can you give you 91? Sorry, you can check here. So basically, this is, I give you a correct witness, and then when you can generate a proof using the witness data here. And this will output a proof. Okay, so this, so far, it will generate the proof. That's also how you see, why you have to generate proof, because somewhere you have to give the witness data, the inputs. This is pretty much almost like the way to simplify it. You can almost think about, hey, this is the step you plug in all your inputs from the verifier. And once you have that, you can generate proof. So these 2 steps produce a proof. Make sense? Okay, the last step will be just verify it, right? You can verify it natively. Basically, you can run it locally. That's how you do it. ZoKrates, just verify. You can even play it here. I mean, afterwards, you can play with this. So because this is actually a factorization of 91, so this is going to return true, right? So if you, let's say, change that 7 to 6, and this thing will fail. So once you, even though you can produce a proof, this thing is going to fail because, you don't know. These 2 are not the factors of N anymore, right? So you can try it afterwards, you can download this thing and try it yourself. But that's not the key. We are interested in this, for the Bitcoin purpose. For Bitcoin, we mostly worry about, how do we verify this proof on chain, on Bitcoin? So you can export, verify it. But instead of the default one, which is give you the solidity version, you can have a ASCII version. So basically now you have the verifier, Bitcoin verifier. And then let's give you, you can use this verifier and you deploy it on chain, then you can verify that's how you verify the ZK proof on Bitcoin. So we already, finished this part. So basically all the complex part is down here. So the only part, the programmers, if they want to use zero knowledge, they have to code the function. That's it. Everything else is, this is the all boilerplate. It's handled by the ZoKrates tool. You don't have to know all the details, but the only thing you have to worry about is, how do I transform the computation I want to produce? How do I code it in ZoKrates? So that makes it, streamlined, right? You don't have to worry about all this detailed theory or, all the underlying math. You can just right now for zero knowledge, you only need to code this like any other, you are doing any other kind of programming. You only have to code the function in this Python-ish, language, and then that's it. Everything else is handled by our tools. Make sense? Any comments, any questions here? And if you really want to get hands dirty, definitely check out our example here. We have I don't know whether can you see this? Now I switch back to browser.
Yeah.
Okay. So basically what I just talked about in the last slide is everything it's more detailed here. So, you can see, how it's more detail. You can say how to install this tool. Once you have it, you can write a circuit, you can compile it, set up, calculate witness, as we talked about, produce a proof. And once you generate a proof, it's going to generate a Python file actually. So it's going to look like something similar to here. This format, you're going to have this. And you can also export a verifier in script. It's going to give you a file called verifier script. So if you know a little bit of our programming language script, you can then use our IDE. It's like any other script smart contract, right? Then you can deploy it. That's how we do it here. You can just right click and say deploy it. Once you deploy it, you can also call it. Basically deploy is just now this verifier is on chain, but then you can also give it some proof for you to run it. Basically you call it. Once you deploy this contract, you can also call it. You can fill out all the parameters here, and then if everything is good, you can call it. And if this is actually a valid proof, this call is going to succeed, right? Otherwise, if there's anything that's not correct here, this is going to fail because the check proof, the ZK-SNARK will only accept the proof if it's actually valid. Means, in this specific case, the P and Q is actually the factor of N. So you can try this, after this session, you can try it. Definitely follow this, step-by-step guide, and to give a really good sense. Just maybe take you 1 hour. You can have your first zero knowledge proof on Bitcoin right now. And you can find this on our blog. It's just, if everything, you can always find script.io and then go to the bottom. There's a medium one. You can always, there's everything about we publish is over here. So if you search about creator first, yeah, it will link you here. I'm also going to put it in the show notes, so you can also find that over there. You can find the ZK rollup example I just covered, but also you can also, find the zero knowledge proof, how to create the first one out there too. Okay. I think we are approaching the 1 hour mark. So here, any closing thoughts, any remarks?
Yeah, for next week, maybe I think it'd be helpful if I kind of did this beforehand. Is there anything you can suggest to do before next week?
Definitely try this out. Walk through this example. This will
Okay.
like, I think it's, yeah, I think it's always the best way to learn is just to do something, just to play with the tools, and then they will give a very good idea. Yeah, definitely play with this tool, and if you have not yet, definitely, you know, try also take this course. So we have the Learn as Script. So we have the ZK Battleship, you know, full tutorial, which walk you through, you know, from zero knowledge to build a real ZK apps on top of Bitcoin with the front end you can interact with. So this is the #1, I think, a tutorial for us right now. So you can definitely check this out. I'm also going to put this in the show notes. So yeah, try this example. And then once you get familiar with the ZoKrates tool, you can switch gear to the ZK Battleship tutorial, walk through these examples. And any questions, we're always in Slack, or you can just ping me anywhere. We're going to help you. Yeah, it would be great if people can, you know, after every session, we're trying to post some exercise out there so people can walk through, and we can, you know, at the end, we're hopeful somebody can watch this and then build some like cool, either demo or even production, you know, ZK apps. That would be ideal. Okay, anything else? Okay, yeah, if nothing else, and thanks for everybody for coming, and I look forward to the next one. Okay.
Cool. Thank you.
All right. Thank you, guys, and I hope to see you next time. And see you. Okay. Enjoy the rest of the day. Okay. Bye-bye.
Bye.
Bye-bye.